So let's do some more examples involving higher order derivatives. In this case, I want to find h double prime of t for the function h of t, so this is the second derivative. Okay, this is the second derivative. So how do we proceed? Well, in order to get to the second derivative, we've got to get the first derivative first. And so we're going to do that. And how can we do that? Well, we can do that with the quotient rule, because I have 1 divided by t plus 1, right? And so I'm going to use the quotient rule here. All right, that's a rule we just looked at in the last set of lecture videos before this one. And so the first derivative, if you remember that quotient rule, it's the derivative of the top function times the bottom function minus the top function times the derivative of the bottom function, all divided by the bottom function squared. Okay? So you need to remember that quotient rule and how to get that. Practice that. Now, the derivative of 1, what's that? Derivative of any constant is 0. Right? That's going to be 0. So this whole thing, 0 times t plus 1, that's all 0. What's the derivative of t plus 1? Derivative of t is 1. Derivative of 1 is 0. Right? Derivative with respect to t is 1. And so up top I just get 0 minus 1 times 1, 0 minus 1. I just get negative 1 over t plus 1 squared. Okay? So now we're ready for the second derivative. Well, I still have a quotient, so I'll do the quotient rule again. The derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. So the bottom being t plus 1 squared. Some of you might be tempted to FOIL out t plus 1 as t squared plus 2t plus 1. I just leave it factored. Just leave it compact. It's easier to deal with down there. Now you could expand it out. In fact, it turns out I'm going to expand it out because technically we've got to be careful. We don't quite have the tools to really talk about taking a derivative of a function inside a function. I've got t plus 1 inside the squaring function. I've got a composition here. We're going to talk about that in the next set of lectures with the chain rule. But someone might say, well, isn't that just power rule? Bring the 2 down and subtract 1 and we're done. Well, that would be the case if it was just t in here, but it's t plus 1. Turns out that bringing the 2 down in front, subtracting 1, does indeed give you the correct derivative, but in general that's not the case, and we'll talk about that with the chain rule. So I'm just going to say here, when I take the derivative with respect to t of t plus 1 squared, right now I do have to expand. So I said don't expand t plus 1 squared, but you will have to expand it really to see what's going on here. This is t squared plus 2t plus 1, right? And now I can take the derivative of this very easily, term by term. Derivative of t squared by the power rule is 2t. The derivative of 2t is 2. Derivative of 1 is 0. And then notice here I can indeed factor out a 2. And so I do get that. So it seems like you say bring the 2 down, subtract 1. You say it works. And why do we go through the process of this? Well, we don't know, and that's not always true that we can do that when we have functions composed inside other functions, and we'll talk about that again, as I said, next time. Okay, well, all that. What do we have here? Oh, what's the derivative of negative 1? We didn't talk about that. That's easy. That's 0. And so this whole thing is 0 minus a negative 1 is what? Plus 1 times this, which just leaves me 2 times t plus 1 all over. What about down here? What's t plus 1 squared squared? Can I do anything to simplify this? Yeah, what do I do with these exponents? What do we do with them? We multiply them. 2 times 2 is 4. Can I simplify this second derivative at all? Yeah. There's a common factor of 2 plus 1 in the numerator and denominator, and so I can cancel one of the t plus 1's rather down here with this one, giving me 2 over t plus 1 cubed. And there is my second derivative. Now if you want the third derivative, we can do it. You have to use quotient rule again, and you'll need to find the derivative of t plus 1 cubed, and you can do it similar to the way we did it for t plus 1 squared. Okay? Let's do another example. This one, not only do I want to find the second derivative, this is Leibniz notation for the second derivative of y with respect to x squared, but this bar means what? This bar means evaluated at what? X equal 1. So I want to evaluate that at x equal 1. So find the second derivative and then plug in x equal 1, see what we get. So here is the function y is the square root of x times e to the x, which I would probably right away think about as what? X to the 1/2 power times e to the x. Okay. So what rule am I going to have to use to find the first derivative? Answer, product rule. X to the 1/2 times e to the x. So the dy dx is the first derivative. By the product rule is the derivative of the first times the second plus the first times the derivative of the second. Now the derivative of e to the x over here, that's easy. We know that's just e to the x. What's the derivative of x to the 1/2 power? Power rule. 1/2 comes down. X to the subtract 1 negative 1/2. Now we could rewrite this as 1/2 times what? 1 over x to the positive 1/2. I'm going to leave it though with a negative exponent right now. My ultimate goal is to just get the second derivative and then to evaluate it. So I can leave it as a negative exponent. If you were wanting to actually give the first derivative right out, you would probably want to rewrite it without the negative exponent, since the original function doesn't have any negative exponents. But what do I have then? This is just equal to 1/2 x to the negative 1/2 e to the x plus x to the 1/2 times e to the x. And I want to leave it in this form to take the derivative of. Now this one here, I have to take the derivative of each piece now to get the second derivative. Second derivative of y with respect to x is written this way, right? d squared y dx squared is the second derivative. So first I'm going to take the derivative of this term and then take the derivative of this term. But when you take the derivative of the second term, we'll notice that we have just done that already, because that's the original function. The derivative of x to the 1/2 times e to the x is this whole thing. But the derivative of this thing is going to be what? It's going to be 1/2 x to the negative 1/2. Let's just group that together as one function. Derivative of that times e to the x plus 1/2 x to the negative 1/2 times the derivative of e to the x. That's the product rule. Okay, so that's this derivative of this whole thing here. Again, so again, product rule. And then, as we said, this one here, we've done. What's the derivative of this thing? It's the original function, so it's going to be 1/2 plus 1/2 x to the negative 1/2 e to the x plus x 1/2 e to the x. So it's going to be all of this. So the derivative of this thing is this, and the derivative of this thing is all this. So we've got a lot going on here, and we're not quite done because I need to find the derivatives of these things. So first of all, notice the derivative of e to the x, again, is just e to the x. And what's the derivative of this thing? I bring the negative 1/2 in front. Negative 1/2 times 1/2 is negative 1/4. And then I have x to what power? Subtract 1 from negative 1/2 is negative 3/2. Okay. So let's clean this up a little bit. The second derivative of y with respect to x, okay, is, I'm going to do a little simplifying as I go. It's this thing here, negative 1/4 x to the negative 3/2 e to the x, that. And then I've got plus 1/2 x to the negative 1/2 e to the x plus 1/2 x to the negative 1/2 e to the x. Notice the x to the negative 1/2 e to the x is the common variable. These are like terms, right? X to the negative 1/2 e to the x, common term, like terms, right? Same variables to same exponents. And 1/2 plus 1/2 is what? 1. So these two here combine together to give me just x to the negative 1/2 e to the x. And then I'll just write this one down here, plus x to the 1/2 e to the x. Notice I can't combine these because the exponent on x is not the same. Negative 1/2 is not a half. So these are not like terms. And of course these are not like terms. So there it is. There is my second derivative. And now, again, you could rewrite this without negative exponents. I'm not going to do that because we want to evaluate this when x is equal to 1. So I can just plug in. So the second derivative, right, of this function, evaluate it at x equal 1. That's the way we write the evaluation. Is equal to what? So I'm just going to plug in 1 here. 1 to the negative 3/2 power, e to the first power, plus 1 to the negative 1/2 power, e to the first power, plus 1 to the 1/2 e to the 1. What do you know about 1 to any power? 1 raised to any power, positive, negative, 0, whatever, is 1. Right? 1 to any power is 1. So these are all 1. Of course, e to the first power is just e, right? E to the first power is e. So this is negative 1/4 e plus e plus e, which equals, e plus e is 2e plus a negative 1/4 e is 7/4 e, or 1.75 e. Right? And that's what we want. We want an exact answer. You can approximate this with your calculator. Oops, sorry. You can approximate that with your calculator, but that's the exact value of the second derivative evaluated at 1, and that's what you want to do. Okay, so again, higher order derivatives, not that bad. You're getting good practice with using all the rules that we have developed so far for derivatives: constant rule, constant multiple rule, sum and difference rule, power rule, rule for the exponential, natural exponential function e to the x, and then of course the product and the quotient rule. All right, close today with just this lecture with a little example here. This is sort of a mathy type of question, but every now and then it's good to stretch and to think about things a little bit. And this is going to introduce a topic that you should be familiar with as we solve this problem, and we'll talk about that. But here's a function, and a and b are some constant value, some real numbers, and we're to find those two numbers, a and b. What are the values of a and b, such that f prime, the derivative of this function, evaluated at 1 is 21, and f double prime, the second derivative of this function, evaluated at 1 is 30. Okay? So how do we proceed? Well, we're going to need the first and second derivatives, so let's find them. Remember, a and b are constants. So when I take the derivative of ax cubed, a is a constant, it comes out, and I bring down the 3, so I get 3a, and x what? Subtract 1, 2. So a is a constant, so whatever a is, I multiply it by 3, subtract 1 from the exponent 3 to get 2. Here I bring the 2 down, I get 2b times x. The derivative of 3x is 3, the derivative of 1 is 0. There's my first derivative. And what do we know? F prime of 1 has to be 21. Well, what is f prime of 1? Well, if I plug in 1 for x, remember x is the variable, a and b are constants, I get 3a plus 2b plus 3. And notice in the problem, we want f prime of 1 to be equal to what? 21. So this gives us an equation that 3a plus 2b plus 3 is equal to 21. Or if I subtract 3 from both sides, 3a plus 2b is equal to 18. Okay, so there's infinitely many possible values of a and b that satisfy this equation. So to find the values of a and b, we're going to need more information. What is the other information? The second derivative at 1 is 30. So let's go now find the second derivative. How do I find the second derivative? I take the derivative of the first derivative. So what's the derivative of the first derivative? 3a x squared. What do? I bring the 2 down. 2 times 3 is 6a x to what? The first. Subtract 1. The derivative of 2bx is just 2b. And the derivative of 3, a constant, is 0. So there's my second derivative. And here I have, again, the second derivative evaluated at 1. Is just 6a plus 2b. And so what do we need to have? We need to have the second derivative evaluated at 1 to be equal to 30, according to this. So the second derivative at 1 is 30, and that's going to give me 6a plus 2b is equal to 30. Okay? And I have a second equation. And what we have to do then is what? To find the values of a and b that satisfy both of these equations, we have to solve this, what we call what? A system of linear equations. Okay? And so this is something you should be able to do. You've either solved systems of linear equations by, say, substitution or the addition-elimination method. If you want to investigate systems of linear equations a little more in depth, after you take Calculus 2, you can take linear algebra with me. We do the more in-depth investigation of systems of linear equations, and we use matrix methods to solve them. But here, you should be familiar with how to do this. I'm going to show you here one way I can do substitution. So notice I can solve both equations very easily for 2b. So there's lots of ways you can solve this, and so you can, if you know how to do it a different way by elimination, you can. I'll do a little bit of sort of a substitution. But notice in the first equation, 2b is 18 minus 3a, right? If I just subtract 3a, I get 2b is 18 minus 3a. And here, if I just subtract 6a, I get 2b is 30a, right? And so what do we have to have true? 18 minus 3a, which is 2b, must be equal to 30 minus 6a, which is 2b. And so I can solve this equation now, which is an equation in only the variable a. So I'm going to be able to find out what a is. Okay. So if I add 6a to both sides, negative 3a plus 6a is 3a. And if I subtract 18 from 30, I get 12. So I'm going to add 6a to both sides, subtract 18 from both sides, I get this. And of course, if I divide both sides by 3, I get a is 4. Now I can take, how do I find b? Well, I can find b by plugging into either of these equations. So I'll find b, oops, b is lowercase, find b by plugging in into the first equation. And the first equation was 3a, 3 times 4, plus 2b is 18. 3 times 4 is, of course, 12. If I subtract 12 from both sides, I get 2b. 18 minus 12 is 6. And so what is b dividing by 2? 3. Right. So these are the answers, right? A is 4, B is 3. Those are the values that will make the required values of the first and second derivatives evaluated 1 to be 21 and 30 respectively. Okay? And if you want to check now, you can plug in, you can rewrite the original function, right? We said A was 4, so this would be 4x cubed, B was 3 plus 3x squared plus 3x plus 1. We now just take the first derivative, plug in 1, we should get 21. Find the second derivative, plug in, we should get 30. Okay? So problems like this will prop up every now and then just to get you thinking about things. So there are some algebra techniques that you need to maybe review, thinking about solving simple systems of linear equations. Finding all the values of a and b that satisfy both equations is what we've just done. Okay, we'll stop here, and our next focus will be on the chain rule. Very, very important. And we'll look at that next.